Autonomous vehicles do not operate in closed environments. They navigate an open world, reacting in real time to erratic pedestrians, complex intersections, and blinding weather. These 2-ton vehicles carry massive kinetic energy. If a system maneuvers incorrectly, the resulting force is destructive. In ISO 26262 terms, the severity, S, of an accident cannot be 0. Furthermore, unpredictable open road variables guarantee controllability, C, also remains above 0. Since severity and uncontrollability are physical absolutes, every autonomous system carries an inherent residual risk that cannot be engineered away. Acknowledging that absolute zero risk is impossible creates a difficult engineering dilemma. Developers must determine exactly when an algorithm is safe enough for public roads. Without a threshold, teams enter an infinite testing loop, pushing object detection from 99 to 99.9% without a finish line. SOTF Clause 6 solves this by forcing the engineering team to establish a rigid stopping rule. These acceptance criteria act as hard, quantifiable exit parameters. They mandate precise statistical targets, restricting specific crash rates to 10 to the negative 7 per hour. Defining this target mathematically proves safety, ending the R&D cycle and establishing a commercially viable product. To calculate that exact stopping point, safety architects rely on 4 established risk evaluation frameworks originally developed for the aerospace and nuclear industries. The first framework is GAMB. This requires the new machine to be statistically safer than the existing baseline, in this case, the human driver. However, proving human-level safety at a 95% confidence interval requires a vehicle to drive over 2.75 billion physical miles without a fatality, which is logistically impossible. The second philosophy is positive risk balance, or PRB. This permits the introduction of new machine-specific errors, like phantom braking, provided the system eliminates a vastly larger number of human-caused accidents, creating a net gain for society. The third is ALARP, as low as reasonably practicable. This principle halts further development when the financial cost and time required to fix a rare edge case grossly outweigh the actual safety gained. The final framework is minimum endogenous mortality, or MEM. This sets an absolute biological floor, demanding that autonomous technology never increases a person's natural probability of death. Open-world driving involves too many variables to rely on a single metric. Attempting to validate a system using just one of these philosophies creates critical vulnerabilities in the safety argument. Industry leaders resolve this by combining all 4 frameworks into a multi-layered safety argument. At the highest level, they use GAMB to set the macro target. This assures regulatory bodies that the complete system outperforms human baselines. In the middle layer, they deploy PRB to legally and ethically justify deployment, even if specific sensor perception limits remain unresolved. At the engineering level, they use ARLP to decide when to stop adjusting the algorithms and instead restrict the operational design domain. For example, automatically disabling self-driving functions in heavy snow. Stacking these philosophies provide manufacturers with the logical architecture needed to confidently declare their systems safe for public launch. SOTIF guidelines require the software to behave like a competent and careful human driver. The challenge lies in translating those qualitative human traits into strict computable mathematics. Intel's Mobileye addressed this by creating responsibility-sensitive safety, or RSS. This equation calculates the absolute boundary for collision avoidance. It forces human caution into a strict minimum safe distance metric. The variable ρ formalizes reaction time. It codifies a careful driver by restricting the hardware's processing delay limit, requiring the system to compute and react between 0.6 and 1.5 seconds. The variable a represents deceleration. This establishes a biologically reasonable braking force, defining the exact mathematical difference between a comfortable stop and an aggressive emergency maneuver. If an external object suddenly breaches that calculated safe distance, the algorithm must execute a predetermined proper response rule. The AI is stripped of its guesswork and forced to comply with the math. SOTIF acceptance criteria operate as hard-coded kinematic physics. They directly govern the vehicle's steering and braking actuators. These calculated parameters do not exist in isolation. They must align with rigid regulatory baselines. The UNEC Regulation 157 for automated lane keeping systems mandates specific maximum deceleration values between 4.0 and 6.0 meters per second squared. These figures serve as the absolute hard constraints for the SOTIF math model. Beyond the law, consumer rating bodies like Euro NCAP dictate market viability, setting the commercial targets for SOTIF validation. A Euro NCAP safety test, like a pedestrian crossing at 50 kph, acts as the physical manifestation of the safe distance formula. If a manufacturer's SOTIF criteria allow a looser response than Euro NCAP protocols demand, the vehicle will fail commercially. These external benchmarks act as the ultimate anchor for the algorithm's design. The combination of physics, philosophy, mathematics, and regulation is finally compiled into the mandatory work products required by ISO 21448 Clause 6.6. The first output is the vehicle-level hazard list. Unlike traditional hardware failure documentation, this isolates the specific risks created entirely by the algorithm's performance limitations. This matrix plots the frequency of exposure against severity and controllability. The shaded zone defines the system's residual risk. The final output is the acceptance criteria document, establishing the rigid threshold dividing allowable error from unacceptable failure. Together, these three documents form the baseline blueprint. Without them, the remainder of the safety lifecycle lacks direction. The Clause 6 work products serve as active data inputs, feeding the SOTIF V-model pipeline. They flow into Clause 7, where engineers perform a gap analysis, measuring current error rates against strict new targets to identify required functional modifications. The criteria also determine the Clause 9 validation and verification strategy, dictating the exact volume of digital simulation and physical test miles required to prove compliance. Safety in autonomous driving doesn't end here. It relies on a dynamic, continuous mathematical argument built upon precise, uncompromising thresholds. Now that the absolute boundary of safe operation is defined, developers face the primary engineering challenge: hunting down those deeply hidden, unknown triggering conditions in Clause 7 that constantly threaten to completely break the mathematical model.